Hello, I'm Mr. Homer, working at London Brookes College. I want to show you the CPAC Practical 1 for Chemistry. This is an acid-base titration. The point of a titration experiment is to determine the concentration of a solution whose concentration is not known accurately. In this vessel here, I have some sodium hydroxide solution. You'll realise that's an alkali. And I'm going to react that alkali with an acid. The acid is sodium hydrogen sulfate. I'm going to make up that solution very, very accurately by weighing out a mass and making up a solution in a volumetric flask. From the volumes reacting and the mass of the solid I use, I'll be able to do a calculation to determine what the concentration of the alkali was at the beginning.
I'd like to introduce you to the apparatus that I'll be using in this titration. Some of the equipment here is designated as volumetric equipment. The first piece of equipment I want to show you is this glass burette here. A burette is designed to deliver volumes of liquid from 0 all the way down to 50 centimeters cubed. The smallest divisions on the burette are in 0.1 centimeter cubed, but it's possible for us to read to half a division, so I would expect students' results to be to 0.05 centimeters cubed. So that's a burette, and we operate it with the tap there. I'll show you that shortly. Another piece of apparatus is the volumetric flask. The flask is designed to measure one specific volume, 250 centimeters cubed. There is a graduated line put onto that flask there. You can see it near the top of the neck. And when I bring the liquid up to that line, that means the vessel contains exactly 250 centimeters cubed of liquid. So that's a quarter of a decimeter cubed and a quarter of a litre. Another piece of apparatus for measuring one specific volume is the volumetric pipette. Again, it has a single graduated line. When I fill the apparatus up to this line here, I've measured out 25 centimeters cubed, and then I can let it run in. So that's the volumetric apparatus. I'm using standard laboratory glassware, conical flasks, beakers, etc. One other very precise apparatus is the top pan balance. This balance measures to 2 decimal places, in other words to hundredths of a gram. I expect the students in this practical to measure the mass of the acid, the sodium hydrogen carbonate, as precisely as possible. The first part of the experiment I'm going to do is to make up a solution of the acid sodium hydrogen sulfate. You'll see that I've now got into my health and safety gear now, wearing a lab coat, goggles and protective gloves. All of this is best practice to protect myself from chemicals such as this here. Even small amounts, if that gets on your skin or you touch your eye, you are going to have some trouble. So please do follow health and safety instructions. I'm going to make that solution up. I'm then going to make it up into this volumetric flask here. I'm then going to carry out a titration by putting the sodium hydroxide in the burette. I'm going to make up my acid solution, my sodium hydrogen sulfate solution. I'm going to make it up into the volumetric flask. I'm aiming to have that solution about 0.1 moles per decimeter cubed. From the mass I used, I'll be able to determine exactly what its concentration is. So when I say approximately, I will be able to calculate exactly what it is. So to achieve about 0.1 moles per decimeter cubed of the acid solution, I want 3 grams of the solid weighed out. Right, there's a series of weighings here. Now, can I stress to students that you should write your masses down as you take them? Invariably, errors are introduced by students walking around the room trying to remember numbers and they get it wrong. Have your lab book with you and write these down as you take the measurements. This is a weighing boat. I want to know what the mass of that weighing boat is, so write it down straight away. The boat weighs 0.95 grams. I want to measure 5 grams of the acid. I'll aim for 3.95. If I achieve that, I will have exactly the 3 grams. If you find in the middle of this process that you spill any of the solid onto the top of the pan there, you need to remove that because it won't end up in the solution. At all stages here, you must give it the best possible standard of work. So 3.95 I'm aiming for. I'm nearly there now. Right, it didn't have to be exactly 3.95 as long as I know what I have got there, and that is in fact 3.95 grams. You'll notice that I'm wearing my gloves and my goggles to protect me from this solid acid here. Now transfer that solid acid into the beaker. It's possible that some of the acid might have remained in the weighing boat, so I need to put that back on there and weigh it again and just check what the mass of that is. In fact, it has come back to the original 0.95 grams, which means that I have transferred all of my 3 grams into the beaker. Exactly 3 grams has gone into the beaker. Now ready to make a solution. I've got my data written down now, so there's no errors introduced by trying to remember the numbers. It's most important that you keep all of the solid and then therefore all of the solution in that beaker. This is deionized water. I'm going to take the top off so I can quickly introduce about 100 centimeters cubed of water. This is virtually pure water. Don't be too fussy, just approximately 100 on the scale there is fine. This compound is a sodium compound, and as you may be aware, all sodium compounds are soluble, so it will dissolve down. You might need to be a little bit patient. You might need to crush the crystals down a little bit. You cannot proceed until we've got this completely dissolved down. As I say to students, when you do titrations, if you're in a hurry, you really should not be doing a titration. You need to give every stage the appropriate attention and care. As soon as you introduce errors, then those errors will come out in the answer not being as accurate as we wish it to be. So it's dissolving down, it will get there. So my solid acid has now completely dissolved into the water. I want to transfer it into the 250 centimeter cubed volumetric flask here, and you need to be very careful with the steps involved here. You don't even consider trying to deliver it straight from there into the top. You put a filter funnel in the top there and then transfer it across. By the way, all the glassware should be cleaned prior to the experiment, so just transfer that in. Not too hastily, it could overflow. Right, there is residual solution in that beaker and on that glass rod, so you rinse down the side of the glass rod, and that will transfer any of the solution back into the beaker, into the body of the solution remaining in the beaker. So I think that's now clean. And then if you just irrigate around the side of the beaker, you're washing all the solution into the bottom. Then I can transfer it into the flask. Right, for good measure, we can repeat that procedure. Rinse around the side so I get any theoretical acid transferred to the bottom. All right, I'm very confident now that all of my solid acid has been transferred into that flask. Right, the next stage is to bring the water level up to the graduated line. Remember, that's 250 centimeters cubed, and it's very important that you take care with this, because if you do mess it up, you actually need to start the whole procedure again. So I'm going to pour it in from the bottle. Don't worry about, sometimes I see students trying to fill these things up like that. It's better if you just take the top off and quickly introduce the water. But don't be too hasty. I'm going to stop well short of the line for a good reason. Disasters that can happen with titrations, very, very easily you can overshoot that line. You know, you think you've got control of it and suddenly overshoots the line. If you do overshoot the line, you've got to start again. You've got to weigh out your solid and start again. So let me just take that out. So you can see that the liquid level is here and the graduated line is there. I could add a little bit of liquid with the wash bottle. I find that rather risky. Very, very easily I could overshoot the line. So that the safest, best way to get it up onto the line is go back to that beaker, the one that we were using, put a little bit of water in there. And I want to get the meniscus, which is the curved surface on the top of the water, I want to get it just sat on that line. Because of surface tension in water, the surface is called the meniscus and it bows down. It bows down. I need to have the bottom of that curved surface touching the line, okay? So it just bows down and touches that line. So we need to do this dropwise, and really you need to get out of your chair, get down, get perpendicular and add it a bit at a time. Now this should take you 2 or 3 minutes to do this. If you overdo it, you can't take the water out again. You've intrinsically made it inaccurate. So a drop at a time. It's a good idea at this point to ask your teacher just to confirm that you are on the right level at this point. Very often when I walk around the laboratory, I find students are still too low. Their liquid level's too low. It's on the line, but it's not just touching, bearing down onto the line. So the curved surface should be sat above, just touching the graduated line. Now I think that is perfection at the moment. So my total volume of liquid is 250 centimeters cubed. Those of you that think about these things realise that it's actually a little bit less than 250 centimeters cubed of water. Question why? And the answer to the question is because there was some solid in there as well. So theoretically, it's just a smidgen below. But the volume in there is 250 centimetres cubed. Right, this needs to be mixed because at the moment it is a heterogeneous solution. That means the concentration is not consistent throughout the vessel. So stop it on, put your thumb over the top and invert it 2, 3, 4 times. It's not a cocktail. Shaking it will not effectively mix the solution together. So just put your thumb over the top and use the air bubble to do the mixing. Okay, so now I've got a completely homogeneous mixture. That means the concentration is constant throughout. Okay, you might see that the liquid has dropped slightly below the line. That doesn't matter because some of the liquid has got trapped around the bung. But I think I've done that to the best standard we could do. The next task is to fill the burette with the sodium hydrogen sulfate. This is the solution we've just made up here. I'm going to put this into the burette. Right, now what you should do, you don't know perhaps what was in that burette before we did this experiment, so you should, it's good practice to rinse the burette out with a little bit of the solution. If you just put a little bit of it in there, and we have a fresh funnel. I usually stand up to do this. I find that you've got better manipulation if you stand up. And make sure the tap, by the way, is closed. The tap is closed there. It's like a bar going across. Liquid can't go through. So I'm just going to put a little bit of liquid in there. Not too much. Take that out. And then if you just carefully rotate the burette, then that washes around the inside with the sodium hydrogen sulfate solution I've just made up. Be very careful with this. You need to practice this so it doesn't run out at the end. Okay, you can see that I'm gradually teasing it up towards the top end of the burette. Okay, so that's a very well rinsed burette. The solution that I'm going to put in it is being rinsed through. I'm going to designate this beaker now as a waste beaker. A good tip, by the way, because you've got so many bits of glassware and lots of colourless solutions, let me put waste on the side of this beaker. So I know that if I want to get rid of some liquid, I can just put it into there and then just run it through there because we need to rinse the bottom bit as well. So I need to charge this burette up now with the acid solution, my very accurately known solution. Make sure that that tap is closed. Again, the logic of it, if you think of it, it's horizontal, it's like a barrier stopping liquid going through. I've now rinsed out my burette. I'm now going to fill that burette with the sodium hydrogen sulfate solution. To do that, I need a filter funnel in the top up here, and I'm not particularly short, but that level is quite high there, and if I pour an acid or a hazardous chemical at that height, I think there's a risk of that coming down onto me. So it's much safer if I just lift the retort stand, put it down on that stool, and I'm going to fill it down there. I've got much better access now to the funnel. Right, ensure that the tap is closed, and I'm going to fill the burette with my sodium hydrogen sulfate solution. Don't be too hasty. I see many students just rush at this point and the liquid flows over the top and it's a mess. So I want you to deliberately take it above the 0 line. I've now passed the 0. Right, I'll be saying this several times, remove the filter funnel. You must remove the filter funnel before we proceed with the titration. Right, it's now above the 0 because there may be some air bubbles trapped down the bottom there. So you cannot proceed with the titration until you get rid of any air at the bubble. You see there's a little trail of bubbles? You must expel those. Now sometimes students say, oh, I couldn't get rid of that air bubble. You can't proceed until you get rid of that air, and just come and talk to your teacher if you're having problems with that. But it must be a continuous column of liquid now from the top all the way down to the tip of the jets. So I'm just going to run that down into my waste beaker so that the bottom of the meniscus sits on the 0 line. Okay, that's perfectly there now. Right, we're about to do the titration. Please ensure that burette is vertical, so look at it in one plane and then the other plane, ensure that it's vertical. Make sure that nothing is loose and that it's in danger of slipping down. Sometimes people don't clamp it well enough and it can slip down. I'm pretty happy with that at the moment. I've got my acid in the burette. I know its concentration very accurately. The next job is to put my sodium hydroxide solution into a conical flask. Remember, this is the solution I'm trying to find the concentration of. I'm going to use this volumetric pipette here and transfer 25 centimetres cubed into that conical flask. This type of pipette filler, it just needs a small amount of pressure just to engage the glass with the top of the pipette filler and make sure that that's fully depressed. Right, this is going to draw up. If I rotate the wheel, it's going to draw up the liquid for me. So this is my sodium hydroxide solution. I'm drawing up 25 centimeters cubed. Here's the line. I want to go over the line, and what I recommend you do is to flip off the filler and then just rotate it steadily, just very, very slowly. You'll find the air leaks around your finger and you can bring it down so that the meniscus sits on the line. It's quite bowed, that meniscus, and it's now just touching the line. Oh, I think that's pretty well on the line. I'm happy with that. That's going to be transferred into the conical flask. Okay, so this apparatus delivers 25 centimeters cubed. No need to try and blow that residual volume. That's designed to stay there. You just touch it like that, and that's now delivered 25 centimeters cubed. I've got my sodium hydroxide, I've got my sodium hydrogen sulfate in there, and I'm ready to start the titration. Just a quick word, these fillers, I remember a time when people didn't use fillers and they actually used their mouth to draw up the liquid, which seems precarious to me now with the solutions that we use, but that used to happen. Okay, another word on health and safety. I have seen several students cause an injury by engaging the filler with too much force where the glass is broken and a shard of glass has actually gone into their hand. I've seen people make that mistake, so be very careful. It only needs to go in a little bit, about a centimetre like that. Okay, I'm now going to proceed with my titration. I need an indicator. This is phenolphthalein, and I'm going to put a couple of drops into my sodium hydroxide solution. Okay, so it's quite a strong pink or magenta colour is the probably better term for it. So it's alkali. You might make the mistake of thinking it would be red in acid. This one is red in alkali. That shows me that I've got an alkali in the conical flask. Right, I'm ready to go. Just check again that the meniscus is on the 0 line. If it has slipped down, if a drip has collected there, you need to rectify that and bring it back up. Remember that you put the funnel in the top to fill it, and then you remove the funnel. You might need to bring the level down again. But I'm happy with that. I think that's ready for the next stage. This first titration, we call it a rough titration. It's just to establish the region where the neutralization will occur. The point where the neutralization occurs is called the end point or the equivalence point. And at that point, the alkali and the acid have completely reacted together according to the chemical equation. So I'm after that spot-on moment called the end point. This is a rough titration. I'm going to add the liquid fairly swiftly, but don't just let it run in. I'm running acid in. Phenolphthalein, I think it's probably my favourite indicator because it gives a very, very discreet, very distinctive final change. So it remains pink, so about a centimetre at a time in the rough titration. Now, unlike universal indicator, which will be changing colour subtly throughout, this holds the magenta, the pink colour in the alkali until it's neutral. And then it's like a switch flicking and you'll see what colour it goes once it reaches neutral and then slightly acid. So it's still alkaline. You can see locally in the middle at this stage of the rough titration that it's going colourless in the middle. You see that's just going colourless. That gives you a little clue to what might happen next. So it's slightly colourless in the middle, but then when I swirl it, the pink colour is restored. It's still alkaline overall at the moment, but we're about to change, I think. Right, very good. That's now decolorized completely, and that colour solution is my end point. Right, I need to read this off to the nearest half division. You can see it's below 25, 23.5. It's actually on about half a division. It's about 23.55. I don't think it's on 5.6, 23.5. Next step, write that down straight away, 23.55. I'm drawing up a table in my lab book here, and my starting volume, by the way, another very key point, can you write 0.00? Should be 2 decimal places throughout this table. Don't just write 0, you'll incur a penalty point. 0.00, and now it's 23.55 is the rough end point. Okay, that tells me the region of the more accurate version I'm going to do next. So that was a rough titration, but it gives me the ballpark of where the end point is. Okay, we're now ready to do the first accurate titration. I've just transferred 25 centimeters cubed of the alkali, the sodium hydroxide, into a fresh conical flask. I could use the previous conical flask and rinse it out with deionized water. You don't need a dry conical flask to have a very, very accurate result. But for the purposes of this experiment, I'm using a fresh, clean conical flask.
flask. Just a reminder, the health and safety for the sodium hydroxide, I use the pipette filler and ensure that you don't put too much force and break the glass, because that could be very hazardous. So I've got my sodium hydroxide in here. I've got my acid, my sodium hydrogen carbonate. I've just topped it up, and it's the top of the meniscus is just sitting, just bearing down onto the 0.00 line. If there's any sag in that, if it's dropping below the line, you need to bring it up again. The indicator I'm using, I'm adding phenolphthalein to the sodium hydroxide, and we can see the very vivid pink or magenta colour. By the way, you certainly don't need to add more indicator, but if you add a lot of indicator, indicators are actually very, very weak acids. If you pour half a bottle in there, you will start to impact upon the accuracy of the experiment. So I don't think you can be a bit cavalier by how much you put in. Just a couple of drops will not impact on the accuracy. So I'm ready to do my accurate titration. So it's on 0, I'm going to run it in. Now my endpoint previously was 23.55. I can run in the liquid quite quickly now, and I'm going to come down to about 22 centimetres cubed. And then I'm going to take things much more steadily. I'm recommending that we wear goggles, health and safety, but you will find that you need to remove those to get a good reading on the burette. So I'm coming down to about 22, swirling all the time. You must swirl a bit. I think at this point I'm not going to worry about flask, I'm just going to worry about the liquid level up there. Right, I'm about 1 to 2 centimetres from the end point. Now at this stage I need to very, very carefully add liquid from the burette, the sodium hydrogen carbonate. Just add that a drop at a time with swirling. This is a moment where you need maximum patience and maximum care. The ideal is that you hit the spot where one drop decolorizes the solution. Now I see students at this point, they maybe get a bit tired and then they add it too hastily and they don't get a very crisp end point. I added it quite quickly down to about 22, but this is very, very slowly now. A titration like this reminds me when I was a student at university that we were trying to get the best accuracy possible, and there were prizes given for the best titration results on the course. Just a drop at a time, then I can quickly stop the tap dripping. Still just a hint of pink there, just a hint. That's now just decolorised. Because I did it slightly more slowly, on 23.50, just about one drop less than it was before. So that's my accurate result. Write it down straight away, 23.50. So that's my first accurate. Right, I need to do a second accurate because I need to achieve concordant results. I need to do another titration, and it should really have the two results should be the same. The two accurates should be the same. We're doing the same method, but I need to check what the result is and do a second accurate and take the average of those two. When they agree within 0.1 centimetre cubed, we say that they are concordant results.
We've now completed the titration experiment. We did a rough titration. You saw me doing the first accurate, and then I went on to do a second accurate off camera. These two values for the first and second accurate, here they are, 23.5, 23.4. We say that these are concordant values because they agree within 0.1 of a centimetre cubed. So I need to achieve concordancy. I do not use that rough figure to work out the average here. If these values are not agreeing within 0.1, I need to do a third accurate titration, do it again, and get two that agree within 0.1 centimetre cubed. So don't be afraid of doing an extra one if you need to. So there's my data in the table. Everything's to 2 decimal places. Even at the beginning, put 0.00. Right, just reflecting overall what's happened in this equation, an acid alkali giving a salt and water reaction. My mass weighings for the sodium hydrogen sulfate, here they are to 2 decimal places because that was the precision provided by the top pound balance. So I used 3 grams of the sodium hydrogen sulfate in the experiment. Remember, the aim of the experiment, we're going to determine what the concentration of that alkali is shortly. Always put down which indicator you've used and what the colour change was in the indicator. It changed from pink to colourless at the end point. We'll now progress on to the calculation. Here's the chemical equation, and I'm now going to work out what the concentration of the sodium hydroxide was. We made up an accurate solution of sodium hydrogen sulfate in this 250 volumetric flask. Well, the moles of that, moles of the sodium hydrogen sulfate equals the mass divided by the molecular mass. You recall that I use exactly 3 grams, and the molecular mass of the compound here is 120.1. 0.02498. That's the moles of the sodium hydrogen sulfate that I used. The concentration of this in that flask of the sodium hydrogen sulfate equals the moles divided by the volume in decimeters cubed. Well, here's the moles of it, 0.02498, and that is 0.25 decimeters cubed, and that equals 0.0999 moles per decimeter cubed. So I've got the concentration of the sodium hydrogen sulfate. It is nearly 0.1. It's just a smidgen off 0.1, 0.0999, the concentration of this. What I want to do now with the chemical equation, I want to work out the moles of the sodium hydrogen sulfate I used in one titration. So the moles in one titration equals the volume concentration times the volume in decimeters cubed. Okay, I've just worked out the concentration here, it's 0.0999, and the volume of the sodium hydrogen sulfate was the tighter figure. This was the final figure, which you'll recall my average was 23.45. That isn't correct at the moment. That needs to be converted into decimeters cubed by dividing it by 100. So this is the moles of sodium hydrogen sulfate in one titration, 2.343 times 10 to the minus 3. That's my moles of sodium hydrogen sulfate. The chemical equation tells me these react in equal numbers of moles. Okay, so therefore the moles of sodium hydroxide in one titration is the same. These are equimolar in the equation. So this is the moles of the acid, so the moles of the alkali is exactly the same. So I 2.343 10 to the minus 3 moles. And the very final step is then to calculate what the concentration of that sodium hydroxide is. Concentration equals moles divided by the volume in decimeters cubed. Okay, I've just established that the moles is the same as the acid. Here it is here. So it's 2.343 10 to the minus 3. The volume now, 25 centimeters cubed. Remember, I used 25 centimeters cubed of the alkali in each titration. I'm just considering the moles in each titration. So 25 centimeters cubed is the same as 25 times 10 to the minus 3 decimeters cubed. Or you can write 0.025 if you want, 0.025. That's the final answer then. So my sodium hydroxide concentration is 0.0937 moles per decimeter cubed. This is what I was trying to find. I've now established that as 0.0937 moles per decimeter cubed. We've completed a very successful experiment here. Just I want to quickly recap on a few points that will ensure that you get very good results yourself. Make sure that you've got no airlocks in your burette. Always remove the filter funnel from the top of the burette. I see a lot of penalty points when students do assessments. They forget to remove that. The volumetric pipette, be very careful with the pipette filler that you don't have any accidents with that. Put all your data down to 2 decimal places or 3 significant figures for your final answer. I'm very pleased with what we've done today. That's all gone very well, and I wish you lots of success, practice that you have doing acid-base titrations. Good luck.